Tsinghua University. And it is really my pleasure to give this neural network accelerator design today at ESWEEK education part. So today I will try to introduce the following contents. First of all, I will try to give you some of the background of deep learning and different hardware platforms and how to evaluate, and some design overview of design methodology. And for the second part, I will try to introduce some convolution neural network and the recurrent neural network accelerator. And part 3, I will try to go through the graph neural network accelerator design. So I think everybody is very familiar with deep learning, and the artificial intelligence, artificial neural network is a mathematical model that imitates the structure and function of biological neural network. Many of its variants, such as DNN and RNN, are widely used in many fields. So for example, the image feature extraction and classification, you can use CNN, and the most famous competition is based on the ImageNet, and we can see that with different neural nets, and last year with Transformer, the top one error rate becomes 9.55%. It's really amazing. And it can also be used at very useful real applications, such as the object detections in autonomous driving part. And this shows a typical object detection network with YOLO 5, which has 77.2 million parameters. And you can recognize and detect the cars and the traffic lights and vice versa. And it also can be used at natural language processing. And with the very, very large model GPT-3, it contains 175 billion parameters, and it can try to bring English to LaTeX, which is very useful, I think, for the paper writing. So this is only two very simple examples. And the application of deep learning in the real world is inseparable from three basic elements: the hardware, the algorithm, and the big data. Because we are from the PC era to internet era to the mobile internet era, and lots of data generated. So how can we dig the information from these lots of data is really matters. So for this, the hardware is one of the most important engine and for the deep learning part. Unlike the general purpose processor, which is also the y equals fx, and DNN, or the neural nets, is also one of the forms at a very high level to describe the y equals fx. That means if you cannot write the equation of fx, then you can have you can use plenty of x and y and use DNN training to formulate this y equals fx. So that's why the neural network is widely used, because it represents the very general equation y equals fx. So if you want to have the acceleration of y equals fx, then you just need to accelerate the inference of the trained neural network. So people trying to develop different domain-specific accelerators for the deep neural nets. But for these neural nets training and inference part, from the perspective of carbon footprint, the energy cost of existing high precision neural network algorithm is huge, which directly leads to a very important practical needs for high energy efficiency. You can see that if you are trying to train a transformer with neural architecture search, it will consume a much more carbon footprints comparing with other kind of a human life or American life or a US car, including fuel, lots larger number comparing with all these equivalent carbon footprints. So how to improve the energy efficiency of circuits and systems for the neural nets is very important. So that we need the definition of energy efficiency. Now we can see that that is the performance per energy. That is operations per joule or operation per second per watt. So this is the definition of the energy efficiency. And we need to improve the energy efficiency, especially for the camera applications or the data center applications or the robotics applications. They use a lot of intelligence with the deep learning. So we can see why don't we use the CPU? Why can we use such large models on the CPU? The increase of CPU performance actually is slowing down. It is really difficult to cope with the extremely high performance requirements of the deep learning. We can see that CPU can support some very simple machine learning algorithm, especially for the MNIST, perceptrons, SVM, and so on. So for before 2011, we can see, okay, we can use the CPU for very simple tasks. But after that, more complex deep neural networks and large-scale data sets requires GPU or GPU clusters that shows in this green dots. And we can see that, okay, these GPU clusters makes the accuracy becomes better and better. So, however, GPU is not the only solution because different applications often have different requirements. We can see for different application scenarios, we may need low power or low latency or high throughput. So they really require different hardware supports. So the reality is that the amount of data and the model parameters have grown very faster than the hardware platform. You can see that the data is becoming more and more, but the scaling down is stopped. Maybe now is 3 nanometer or maybe last for maybe a pretty long time. So what should we choose for the deep learning hardware? So we need to design a variety of hardware platforms with different advantages to meet different needs. We can see for CPU, it has very high flexibility, but the energy efficiency is low. And for GPU, the performance is really high, but the power is high, and it's rely on batch. You need to give a lot of data inside and then to do a large amount of parallel. So the energy efficiency is not that good. But for FPGA, it's a field programmable gate array. It's okay power. We can see low power, but the ASIC is lower power maybe. And it's programmable hardware, but it have an average or in the middle performance. It's better than CPU, but it's not as good as GPU. and it's not as good as ASIC. And for ASIC, application-specific integrated circuits, it will have lower power and higher performance, maybe the highest performance if it is customized. And this customized hardware, maybe the programmability and the flexibility is not that good. So the flexibility after tape out may be low. So these are the current 4 different choices for the deep learning training or inference. So from about 2016, we try to draw this figure. We can see we have the y-axis as the speed is GOPS per second, giga operation number per second. That is how many operations you can do in 1 second. So higher the better. And for the x-axis, this is the power, okay? So we can see for, we list about 200 papers and some industry products on this chart. And we put different colors for different platforms. For these are the ASICs, and for these are FPGAs, and for these are the GPUs. And the slash line from the left downside to the right upside is the energy efficiency. You can see this is the 1 gigaops per watt, and this is 1 teraops per watt. So this is 1 teraops per watt. So almost all the FPGA is below 1 teraops per watt, and GPU is nearly 1 teraops per watt, but is larger than 10 watts. And ASICs, most of the publications is lower than 1 watt and is higher than 1 teraops per watt. So this figure shows how we can choose the different hardware parts. But all these are also the ASIC part. So I will try to introduce later on. So we can see, okay, the ASIC has the highest energy efficiency, but maybe the lowest generality or the flexibility. But the CPU has the highest flexibility, but the lowest energy efficiency. So we try to find some XPU part providing high energy efficiency and with strong flexibility. So I think you see a lot of different processing unit with X, NPU, DPU, a lot of different PUs. So we will talk about this part. And how to improve this performance of the different deep learning accelerators. We find out that you need to do the software and hardware co-design. So this is the key methodology we are trying to use during the different neural network accelerations. For a neural network, you need to train a model. So for the design flow part, you need to do the model design first. And then you may use some optimization methodology, such as compression. That means you compress, you make some of the weights into 0. And quantization, that means you make the 32 bits of representation number into 8 bits or even 1 bit of the weights and the internal numbers. And then you, after optimization, you will have the you will design your hardware and do the optimizations between the software and the hardware. And after software, you hardware design, you need to compile the neural network model into different instructions and put it onto the hardware. So these are the design flow, but we can see if you want to have a very high performance and low power of the deep learning accelerator, you need to you make the workload small. That means the total calculation number, the operation number, you need to get to low. That means some of the weights you need to get into zero. So there you will have lower workload. And also if you have 8 bits or 1 bit for the representation of each number in the whole neural network, then the basic multiplier or the adders in your hardware will become a low bit basic components. Then if you given a constrained area, you can put more smaller quantized module inside. So then the equivalent peak performance will become higher. And then we need to bring the efficiency higher, and then you will have the higher performance. So if you want to have higher performance, you will need to get the workload smaller, and you need to put more multipliers into your chip, and then you need to make all the multipliers work when you use the chip. So then with all the together, you will have the better performance and lower power. So these are the key software and hardware co-design methodology. And in the next part, I will try to bring the talk into 2 parts. One is the CNN and RN basis and the accelerator design and some of the ongoing research. And then we are trying to describe the GN part. So one thing you need to notice is that we try to make the sparsity here because we are trying to accelerate different operations. And these operations, most of these operations are matrix operations. And the matrix, inside the matrix, almost about maybe 20% or 40% of the CN or RN are non-zero. But for GN part, the non-zero may be below 1%. So these are the key difference between CN and GN. So we are trying to talk about the CN and GN RN first, and then the GN part. So for the part 2, I will try to introduce the convolutional neural network and the recurrent neural network accelerator design. First we will talk about the basis. So for the convolutional neural network, the convolution is the process of convolving input features and convolution kernels to obtain the output features. The main arithmetic operations are multiplication and addition. So like this figure shows, and the main operation is multiplication and addition, and this feed-forward operation. And this is the very naive 7-layer for-loop implementation of the convolutional neural network. So this is also the simplest way is this loop operations. But calculating the loop directly is very time consuming. So people are thinking about how you can try to change the order of the to compute the loops. And for this part, they are for each output feature map value. And for this part is the convolve window and apply the epic activation part. So for recurrent neural network, the recurrent neural network receive the input vector and the recurrence state and obtains the output vector and the recurrence state of the next time. And the next time recurrence state of the next step after passing through the hidden layers. Therefore, the recurrent neural network is suitable for processing the sequence information. So that's why it's more for some kind of NLP or voice recognition, and so on and so forth. So both long short-term memory, that is LSTM, and the GRU, the gated recurrent units, use gating mechanisms to avoid the forgetting of long-term information. So this gating part is also need to implemented in the hardware part. Okay, so we try to go inside the CN and RN accelerator design part. So as we just explained that the speed equals peak performance improvement and utilization improvement, and the workload decreased. So thinking about if you have a room which only contains 10 workers, then only 10 workers, that is the big workers. So the 10 big workers can do some of the things, but if you, after the quantization, you may put 100 workers inside the same room. And when you do a task, all the 100 people there are only 10% of the 100 people are working. How to make everybody work, that means how to improve the efficiency of and make all the 100 people work is the efficiency improvement. So the peak performance improvement is related to the quantization and hardware design. And the efficiency mostly depends on the compilation technology and the memory design. And the workload mostly depended on the compression part and the quantization, because after quantization, the bandwidth requirement will be lower. So these are the key information you may need to understand. So let's start from the software optimization, because we see that, okay, this is a software and hardware co-design part. So I'll try to introduce the software part first, and then the hardware part technology. So for the software optimization, the first one is the quantization, that is to reduce the bit width. If you can reduce the bit width, then previously you will have a 32 bits multiplier. And after the quantization, you only have 8 bits multiplier. And then you may reduce the area consumption into only 10% of the 32-bit multiplier. So then you can put more multiplier in your chip. So it will improve the peak performance. So people brings different quantization methods, such as linear. Sorry, I made the mistake of linear is not good, and nonlinear quantization. So this is a very useful technology, and everybody now is using that. And the other part is the reduce the model size. Reduce model size. At the very beginning, people are trying to, because this is the neural nets are matrix and vector and matrix multiplication. So for a matrix and a vector, you can use low rank approximations technology, such as SVD decomposition. This is a typical SVD decomposition to bring one big matrix into two matrices. and 1D convolution approximation, or PCA. These are all matrix technologies. And in 2016, Song brings the pruning on neural network neurons and connections. So that means if you have a neural network, and we can make some of the weights into zero or remove some of the neurons during the training procedure. And this will bring maybe we will remove maybe 90% or of the total calculation number, that is the operation numbers of the neural nets. So that will make the workload, that means the total operation number, vary to a very low extent. So the reduced model size is reduce the workload, and that is a very efficient technology that used in the software optimization part. In another software optimization technology is the fast convolution, such as FFT and Winograd. I'm not trying to explain the technology, but you just see that if you're using the Winograd, then you will make the multiplication numbers reduction from 36 to 16. But the overhead is you need to design a different hardware implementation with the typical matrix operation, because you need to be aligned with the Winograd matrix templates. So these are the typical software optimization part. And for the architecture level design, we see that the convolution layer is written as the loop operations. So one of the key problems in hardware architecture design is the loop mapping. So the formula of a convolution layer is as shown as this equation, which can be directly written as 6 loops. What loop mapping does is to break the loop into multiple steps and execute them sequentially on the hardware. So if we want to do the loop mapping can be divided into 3 design points. One is loop unrolling, that is the spatial mapping part. Designing hardware parallelism in all dimension of computing, and it will decide the hardware parallelism in each dimension, and it will affect the peak performance and the utilization ratio. And the second part, second way is the loop interchange. That means the temporal part of the mapping, how to reuse the data and how to decide the on-chip memory design, and that will affect the off-chip memory access. So this is a very important part, because I don't think I put the number here, but remember that if you're doing one multiplication, maybe about only 1 to 1,000 energy cost, comparing with the same data moving cost from the off-chip memory access. So that means if you move a 32-bit data from the off-chip DRAM into your chip, you may cost 1,000 times energy of that the 32-bit multiplication, the multiplier's energy. So if you can cut off some or reduce the off-chip memory access, you will save a lot of energy. And the third design point is the loop tiling. That is how to decide how large the data block size is of each computational task here. And it also affects the off-chip memory access because the data size is related to how large it will have the load and save. So it's also a very important design choices you need to make. So the mapping method described above constitute a large design space. And some work put forward the method of design space exploration. And this paper is, I think, is one of the earliest one. And if you want to see the details, you can go through the papers. And I try to put the PowerPoints on the web and also list the reference paper here. So the loop Onroad strategy should determine according to the hardware complexity and the Onroad parameters can be analyzed and designed using this roofline model. Is computational roof, and computational roof is here, and the bandwidth roof. And bandwidth roof is here. So this is roofline model, and which is a very important model when you design your architecture. So, and for loop interchange and tiling strategy, we optimize them to minimize the external memory access. And one of the key paper is FPGA 2017. They will choose the right loop interchange and tiling strategy and using a very interesting method. And the third is the typical, I try to introduce some of the typical Onroad design. You can see the first one is the Onroad convolutional kernel using the line buffer. That is, you design this kind of buffer design and the input data going through linearly. And they will fully use the reuse the data within a feature map and a convolutional kernel, but it's hard to adjust to different kernel size and stress because you only use this three by three. You just get the 3 by 3 numbers and into the multipliers and the adder tree. So you can only handle the 3 by 3 convolution. And also the second one is Onroad the feature map at the pixel loop, and you will reuse the data within the feature map, and it's quite flexible. And this is a paper published in ESWEEK 2015, and it's flexible to different convolutional kernel size and threads, but it requires a more complex data bus. And there is also a compromised Onroad parameters method is configurable Onroad parameters to maximize the PE utilization with a PE array. It is quite flexible to different convolutional kernel size and stress, but it's the communication overhead on these buses is quite large. So these are within 6 loops. And the other part is typical design choice is trying to use the relationship between the multiple layers, different layers. So loop mapping is the core problem in the design of one convolutional layer. But for the whole neural network, we also need to consider the problem of multi-layer design. You can map with a very large hardware or the large chip or FPGA. You can map all the layers onto the hardware and merge layers as groups and map each group into the hardware. So for example, you can merge three group layers together on the hardware, and then you don't need to get the intermediate feature maps out to the off-chip external memory. So you will save reduce a lot of external memory access. But then you need a very large on-chip memory to store these intermediate feature maps on chip. So for another architecture level design, maybe you can also skip the zero weights at the runtime, because when we use the compression method, you will compress or make some of the weights into zero. So some of the architecture designers are trying to design their architecture, including the functionality of skip the zero weights at the runtime, which is published in the ESCAR 2016. And this is the architecture level. And there are a lot of circuit level design technologies, such as how to reduce the routing cost with the systolic array. This systolic array can be used to reduce the routing cost, and also this multiplication processing engine can skip the zero multiplication and save 45% of the energy. And also they can design different circuits which can handle the dynamic adjusted data bit widths. That means if your data is 16 bit width or the 8-bit width, and then you can also put it into this same multipliers. And in addition, the method of dynamic voltage frequency scaling can also be used to sacrifice the speed in exchange of higher energy efficiency. In addition to computing units, so the previous are all computing units design, the on-chip RAM design is also very important. By designing a multi-layer cache for frequently accessed data, the energy consumption can be reduced by 40%. Since matrix multiplication is a two-dimensional operation, the TSRAM design, the cache TSRAM design cache allows both row and column access, and also improve the efficiency of the whole neural net accelerator design. And in addition to the optimization and the hardware software level optimization and hardware architecture and the circuit level design automation is also a very important technology. Design automation is also corresponds to two levels, software level and hardware level. At the hardware level, the work of design automation is to select the best accelerator parameters for a specific model and automatically generate the computing units with the best parameters by using the templates of or high-level synthesis functions. So this is a typical flow. If you have a model, you change it into a data flow graph, and you put the hardware constraint inside. And for this part, you choose basic function units, and then you change it into a RTL for this model and put this RTL into the hardware. So this flow can be automatically designed, which is very amazing. And another level of design automation, method for design automation is you can use the instructions for more flexible design. So you at the software level, the design automation completes the compilation from high-level neural nets into a set of instructions. You can see for different accelerator, for example, Cambrican or Google TPU or our work at Android, we will have quite similar instruction set. And these compiler will affect the hardware performance, how to change the neural network structure into a set of or a sequence of the instructions in the instruction set, and how to make the instructions, the sequence of instruction smaller or shorter is very interesting. And the data access behavior is very important. It will decide the bandwidth requirement and also the computation unit utilization. So for the instruction, how to design your instruction and how to compile your neural network structure into the instruction is a very important problem. And when you design your own neural network accelerator. So for our previous work, actually, we try to follow to the improve of peak performance and improve the utilization and lower the workload. We designed the whole flow from the Caffe or TensorFlow or other network descriptor into compression, compilation, and the runtime and the architecture design, and put the instructions onto the architecture we designed. So these are some typical papers, and I will not go inside. If you are interested, you can go to read these papers. And we also write a survey on the deep neural network inference accelerators. And there are typical optimization opportunities. As I mentioned, some of them in this talk. And you have the network level, layer level, convolution, and the general matrix and multiplication level, and neural weight level, and also the neural network, not neural network related technologies. And for where to optimize, you can optimize data paths, memory, and also the scheduling part. And some of the technology are for FPGA only, and some are can be used for ASIC. So this is the survey paper. We put it there, and you can also go there and read the survey paper. So I want to show this neural network accelerator comparison website, which I just mentioned in the very beginning of this talk. And we make this chart, and you can choose different phase source and the platform year, support, performance, and sparsity, and activation precision, and or the multi-precision. And you can see different trend. So I'll try to explain a little bit of our findings from the figures. So we put about more than 200 academia papers and 80 industry products on this figure. And most of them are ASICs, FPGAs, and GPUs. And we can see that the three different hardware platforms have relatively obvious range differences. GPU prefers the high computational power and higher power consumption, and with pretty high speed. And ASIC performance low power consumption and high energy efficiency, which is maybe the highest energy efficiency. And FPGA belongs to relatively balanced design. And first, let's take a look at the year-on-year change of FPGA and ASIC platforms. We can clearly see that the energy efficiency ratio of FPGA design is basically below 1 teraops per watt. That is this line, 1 teraops per watt. And where I think the 1 teraops per watt is kind of the boundary used to distinguish FPGA and ASIC accelerators. And let's take a look at the year-on-year change of academia and industry. Sorry. Under different platforms, we can see that the energy efficiency ratio of academia has gradually developed from 10 teraops to 1,000 teraops per watt, while the energy efficiency ratio of the industry has gradually developed from 1 teraops per watt to 100 teraops per watt. There is still a gap of nearly 10 times in energy efficiency ratio between the academia and industry. I think it's because the industry is, the academia is trying to explore the more possibilities. So they are moving towards 1,000 teraops per watt. And as mentioned earlier, the fixed point quantization is a very important neural network accelerator optimization method. Here, we compare and summarize different fixed point quantization bits. One of the most typical trend is that with the decline of the number of fixed point bits, the upper limit of energy efficiency ratio and the decline of power consumption are constantly breaking through. In addition, the industry is still mainly use int8 and int16 to achieve an energy efficiency ratio of 1 to 10 teraops per watt, while the academia community is mainly using hybrid precision and binary network to achieve the energy efficiency ratio of 100 to 1,000 teraops per watt, and is making a breakthrough towards maybe the 10,000, the 1,000 teraops per watt. Okay, so we were also trying to make the development of different ways of the designs. We can see from 2010 to 2015 is mainly the design space exploration. And from 2016 to 2018, there are some mapping tools, low bit widths, and the mathematical optimization work, which is really important. And from 2019 to for future part, we think the trend is structured sparsity, and also they are moving from the inference to training part, and the architecture and the network architecture and the accelerator architecture co-design. And for the ASIC platform in academia, we can see the pioneer is the DNN series. And for after 2016, people are trying to look at the sparsity and the low bit widths and lower power, and from 1 watt to 0.001 watt. And from 2019, there are more applications. I think this is what they are doing, such as scan, video, and SLAM, and etc. And also the compute in memory with SRAM and RRAM, because they can achieve higher energy efficiency, and the dynamic sparsity and the precision, which can also improve the energy efficiency. And for the industry trend, we can see that the application scenario is mainly in the data center in the cloud, and it's about 100 to 1,000 watt and 2 to 3 teraops per watt, and it will have floating point or integer 16 to 8. And for the AI IoT in the edge, it mainly is smaller than 10 watts and 1 to 10 teraops per watt. So they are trying to look at the lessons from the academia, because now we see some startups from the computation in memory, and also they are trying to include some dynamic sparsity. But I'm not very sure about the how they will be used. So it will be very interesting to look into the industry trend. Okay, we know that the next generation of important technologies, the Internet of Things, that is, everything forms a unified organic whole through the cloud, edge, and terminal. And we can see all these parts will include some of the neural network accelerator inside for cars, space stations, cloud, and also the cameras and phones. But these different applications actually means different power. So if you are in the sensor, you need to below 0.01 watt. Maybe if you are using IoT or mobile applications, is typically below 1 watt and typically several hundred milliwatts. And if you are in the camera, is 1 to 5 watts. And if you are in the autopilot or autonomous driving, maybe it's about 10 to 20 or maybe several dozen of the watts. And for data center, you will have maybe over 100 watts. So I'm not you can try to go through all the very typical work at different application scenarios. But one of the trend is you can see that in the industry part, they are making hundreds of teraops within a single chip. I list some of them here, and also some TPU RISC-3 part, and the Huawei SN910 cluster. They put a lot of chip together to bring 512 petaflops data center. And also they have the Cerebras, this wafer scale chip with 1.4 trillion transistor on chip. So in conclusions, we can see that the existing neural network accelerator and AI chips have basically covered the computing power and energy consumption needs of the cloud, edge, and the terminal devices. We can make corresponding choices according to the needs of practical application scenarios. So for a brief summary of the first part, I can see AI platforms are covering everywhere, and we already have many methods and makes the chip powerful and maybe higher energy efficiency. So I also discussing with my student what is the next step, and how we can do inside the university. So we are trying to list two fundamental directions. One is how to deploy this neural network accelerators in the real applications. And the second one is more basic. What is the key information, or what is the methodology of how to carry the information in these deep learning models? So going to the part 2.3, the future directions and some of our case studies. So after we do the typical design, accelerator design, we are thinking about how to use it use the hardware on different applications. So, and the other way is how to optimize on the algorithm. That means how to carry the information. Is the weight carry the information, or the architecture, the neural network architecture carry the information? So we try to look at the application of data center that is for a very, very, very large chip, if how to design the neural network or how to change the neural network accelerator to support multi-tenant, the multiple people to use that chip. Or if you put the accelerator into the robotics part, and they will support different neural nets acceleration on single chip. So you need to, maybe you need to support interrupt. And for the information carry problem, so if we look at the weights, what is the limitation? If you can put it to the only 1 bit, and how if you can train the neural network using maybe 1 bit or 2 bits, that will be very interesting. And also how you design architecture. So how to design the how to efficiently design the neural architecture search algorithm, and how to connect them with the hardware. So these are 4 case studies I will try to share with everyone here. The first case study is using the convolutional neural network accelerator in moving robotics. So the key is how to make the accelerator interruptible. So we, as we all know, that the convolutional neural network actually benefits different robotics applications, such as the feature point extractions, and also the place recognitions, and the object detection. So using the neural nets will have or larger than 10% or even 56% higher accuracy comparing with a traditional method. But if we are only have one deep learning accelerator on your robots, and how to share between 2 threads, that means if you're doing 2 tasks, I will not explain what the task is, but if you're doing 2 tasks and running 2 neural nets, which one is quite small and take that kind of execution time, and the other one is long. So the only one deep learning processing unit need to switch from the low priority task to the high priority task and come back to the low priority task. So the neural net accelerator design need to support the interrupt. So there are 4 stages of the interrupt. The first one is to finish the current instruction and to back up the lower priority task and to execute the high priority task and finally recover the low priority task. So they will have the T latency and the T cost. We are trying to lower both the interrupt response latency and extra cost. So there are 2 ways to do the interrupt. The one way is to interrupt immediately, just like CPU. That means you just stop the calculation as soon as possible, but you need to back up a lot of intermediate data. So the backup and the recovery time will be very long. And the one of the other choice is interrupt after each layer, because neural nets are calculated layer by layer. So after one layer, maybe you only have a very small backup data to need to be safe. So there are no actual backup time, and recovery time is quite small, but you need to wait for a long time to begin the high priority task. So what we are trying to do is trying to find a better place that with more extra cost. So you don't need to wait until the one layer is calculated. So that will I will not explain for the detail, but you're just trying to understand. You don't need to calculate all these data, and you only need to calculate this small part of the data, and the data moving costs will be very low. And simultaneously, you don't need to wait until all these data to be finished. So we test this simple, we change the architecture design and try to test in the multi-level exploration with in this scenario. We find out that our method reaches both low interrupt response latency and extra interrupt cost. And this is CPU-like method brings very high interrupt cost because you need to back up a lot of data. And the layer by layer method, you don't have a very stable interrupt response latency. Maybe some of the layer need to calculate for a long time. So our method achieve a very good results. The second case study, so the first one is more on the embedded part. So I do think there will be a lot of different problems in the embedded part. And I would use another case study on the cloud part. The cloud part, that is, can we use the large TOPS to the extreme? That means we need to share all the TOPS to different users. So how to sharing the large chip or neural network accelerator chip on the cloud is a very interesting problem. So the inference task of neural network occupies a large amount of deep learning task load in the cloud data center. The deep learning inference task of Facebook data center is growing at twice the rate every year. And while the inference task of Amazon data center accounts for more than 90% of the deep learning total loads. So virtualization is very important for cloud data center. It can make physical resources shared by multiple users in the form of virtualization devices, so as to improve the overall utilization of the data center. So how to design this vertical virtualization layer, not only for CPU and GPU, but also for the deep learning processor, is a very interesting problem. So why does the neural network accelerator of FPGA need to support virtualization? The originally designed FPGA deep learning accelerator is usually optimized for single task and static load on the end side or the terminal side, while the cloud task scenario is usually multiple task and dynamic load, which makes the original accelerator unable to meet the requirements of system performance and resource utilization, and will make the performance lower, the whole performance lower of the system. So we need to have a virtualized neural network accelerator design for the cloud part. So let's briefly review the development of cloud AI accelerator and the related virtualization technologies. The first is the development process of GPU. It has experienced 10 years of development from the advent of the first GPU to supporting the multi-user, let me see, the multi-user GPU to be used based on the time division mechanism, multiplexing. In contrast, AI accelerators have experienced 2 orders of magnitude development in computing power since 2014, from several TOPS to hundreds of TOPS. But almost all AI accelerators focus on trying to reduce the delay of a single neural network model. However, the actual cloud scenario is usually multi-user concurrent execution and dynamic load change. The AI accelerator for single task reasoning optimization cannot meet the performance requirements of cloud systems. And so since last year, some of the people are trying to make the multi-user AI accelerators using the time division multiplexing. And we trying to give a method on space division multiplexing. And also people are trying to look at this problem. So I was just trying to show you the problem, and you can look at these papers and they will be a very, very interesting direction you may try to look at. And the reason why we want to expand multi, and also now we are trying to expand the single node virtualization to multi-node virtualization, is that we find out that the reason for this is that we find out that the current models of cloud AI reasoning tasks show a very diverse trend, including megabytes of the very small neural nets, and also the very, very large neural nets. So the cloud AI virtualization system requires maybe the two capability. The first one is we need to break the whole machine into different smaller virtual machines. So to support small models from different users and at different time. And also for the one other scenario is trying to assembling the parts into a whole that is merged across nodes resources to support very, very large network and single task loads. So these are very interesting application trends, and the people are trying to look at them in different ways. And for the other part is what is the key insight of how to carry the information in the deep learning models? So we look at two ways. First way is if we can design very low bit neural nets. So for the very low bit neural nets, people, I do think you can look at a lot of inference neural nets. But now people are also look at how to use the low bit fixed point for training. So the one big challenges of neural network algorithm is that the training is very expensive. We can see that the neural network model contains large amount of calculation, and the storage demand is also very high. And the training process needs a lot of iterations, leading to long time and high energy consumption. Since fixed point units have the advantage of energy consumption and the over the floating point units. So we try to explore the potential of the low bit with training. You can see that the energy and the area differences are so huge. And we find some key issues that because there are trade-offs between accuracy and the energy efficiency. If you are using high dynamic format, you will have higher accuracy. If you use low dynamic format, you will have higher energy efficiency, but low accuracy. So there are three challenges of low bit training. Accordingly, we try to give some a contribution or the technology. I will not go into details, but after if we design it properly, then you can lower the energy consumption from full precision to the our technology of 10 times with very little accuracy decrease. So, but we don't know what is the limit, is the extreme condition of low bit. Is it the 1 bit? And now we are only, actually we are only have, sorry here, the pure 4 bits or pseudo 4 bits. Is it possible to make only 2 bits or 1 bit for not only for inference, but also for training? That will be a very interesting direction for the future research. And for another direction is, can we decide the architecture for new tasks and hardware automatically and efficiently? So that is the neural architecture search. There are many tasks and hardware platforms in the real world. Relying on purely manual design is not scalable enough. So we are curious that can we automate the construction of predictive deep learning models for these tasks and hardware platforms. So actually, we design our own NAS framework and open the NAS framework. We call Awesome NAS because we trying to include a lot of different search strategies and also evaluation strategies. And we include different search spaces and objectives such as the classification, detection, and also maybe fault tolerance, robustness, and maybe energy efficiency, and vice versa. So the framework also connects to different hardwares and the different tasks. So you may look at the hardware. Now we are supporting CPU, GPU, FPGA, and also the new memory, RM simulators. So for this part, we find out that the challenge of the NAS search engine is the architecture search process. That means you need to iterate for a long time in a very large search space. It is very time consuming and resource intensive. And how to make the search process more efficient. So we try to do it in 2 ways. The one way is develop a predictor-based search strategy with very high sampling efficiency. And the other one is we try to use a differentiable sparsity allocation method to improve the pruning efficiency. So these are only our 2 trial method. And for this direction, we are also finding that the high energy efficiency for the neural architecture search is very important and also a very important research direction. And after you have the neural architecture search engine, then how to target the search for specific tasks, even related to the hardware, and also design for the hardware efficiency. So we also try for NAS for the systems safety, such as adversarial robustness and the fault tolerance. And also we try to look at how to design NAS for binary neural networks and also the black box profiling method for hardware accelerators. So these are all, I think, different ways to explore which is important. Is the weight is more important or the architecture is more important? So this is still open, I think the open question at this time. To summarize, we have developed more efficient search strategies, more accurate evaluation strategies to make NAS itself more effective and efficient. And we employ NAS to search for system safety and hardware efficiency related objectives. All the mentioned researchers and other ongoing NAS projects in our lab are built on the AWNAS framework. And we have already open sourced that. So any contributions are very welcome. And if you are interested in either our NAS research or using our NAS framework, and you can email me for a discussion. Okay, so these are a review of the convolutional neural network and recurrent neural network accelerator design technology and some application scenarios and now the future trends. One is from the applications perspective, and the other is from how to carry the information, that how to explore the limit, the extreme of the neural nets. And now we are going into the the third part, graph neural network accelerator. As I mentioned before, the data sparsity is about at the level of 10%, maybe 20% or 30% related to the convolutional neural network or the recurrent neural network in their weight matrix. So the sparsity is quite different here, comparing with the sparsity of graph neural network here. And for this part, the graph we are talking about, because graph is also represented by matrix. So that matrix contains only less than 1% of non-zero data. So actually, a lot of real-world applications or many graphs in the real life, such as the social network, citation networks, moleculars, and neurons. Sometimes we need to handle tasks on these graphs. For example, node classification on citation networks and graph classification on moleculars. Neural networks have strong abilities solving the task on sequences and grids. They target on generating low-dimensional features of the original data. However, traditional neural network models, such as convolutional neural network and recurrent neural network, cannot directly be used for the graph data. When handling tasks on graphs, we also hope to generate low-dimensional features of the nodes. In other words, encoding the nodes to the embedding space is the key function of the graph neural network. So after that, we can use the embedding vectors to represent the nodes and solve the problem in the embedding space. So for example, the node clustering problem can be regarded as a vector clustering problem in the embedding space, and then can be easily solved with k-means algorithms. So now the problem is how to encode the nodes. How to encode these nodes is very important. So as mentioned before, traditional neural nets cannot directly be used for graphs because of their arbitrary size and complex topological structure. Because you can see that image and test is very regular, right? So let's look at the graph. And we can see that the graph data mainly consists of three parts. The vertex set, and adjacency matrix, and the node feature matrix. And the key idea is of the graph neural network is generate node embedding based on local neighborhoods. Researchers propose graph convolution based on the 2D convolution. Actually, it's inspired from the 2D convolution. That this figure shows how you do a 2D convolution, a convolution on the 2D grades. And in graph neural network, the graph convolution is proposed, and researchers use an aggregator to collect the embeddings from the neighbors, and then collecting using the aggregators to collect the embeddings from the neighbors and send out the output to a fully connected neural network. And this equation shows how a multi-layer GNN model with a mean aggregator. So in each layer, the target nodes will get the neighbor's embedding of the last layer and perform the graph convolution. So this is the mean aggregator. So in each layer, the model first performs the aggregation step, and the neighbor's embeddings will be aggregated together to generate a vector for the next step. Then the model performs the transformation step. The output of the aggregation will be sent to a trainable full connected neural network. The results becomes the new embeddings of the nodes of this layer, and so on and so forth. So we can clearly see that there are two procedures or two main components. One is aggregation, and the other one is kind of neural nets, or in this GNN model or the graph convolutional network model, they will contain the aggregation. This is a normalization sum, and the transformation is a single layer MLP. So the GCN was proposed in 2016. In the aggregation step, it normalized the neighbors' embeddings with their degrees and add them together. Then the single layer fully connected neural nets is used for the transformation. And another kind of GNN called graph sage. In the previous GCN model, the numbers of neighbors varies a lot. So we cannot construct batches of the same size. That's why we can only perform full batch training. And when the graph becomes larger, the GPU memory may not be able to hold all the data. To solve this problem, this graph sage only samples a fixed numbers of neighbors for aggregation to realize mini batch training and achieving the same accuracy at the same time. So besides, the graph sage uses a generalized aggregator. They try mean, max pooling, and LSTM aggregators and achieve similar accuracy. So then we were introduced. Now, after looking at the basic algorithm part of the graph neural network, we were introduced the challenges of graph neural network training on GPUs. And in GNN computing, the graph neural network computing, the aggregation step is a sparse, very, very sparse operation. because the node degrees are usually far smaller than the number of nodes. In other words, the adjacency matrix is very, very sparse, but the transformation step is a dense operation because the weight matrix and the embeddings after aggregation are dense. So let's look at the aggregation. And the sparse operation, actually there are two, the sparse operations are less efficiency on the GPU because GPU is designed for dense matrix operations. The figure on the left suggests that in GNN, the aggregation step requires less operations, but more GPU time. You can see the transformation, the flops is larger than the aggregation, but the GPU time, the aggregation is larger than the transformation part because it is very sparse. The right figure shows that the computation capability of different operations. You can see that GMM dense and the GPU is very close to the GPU peak performance. But if you look at the very sparse operation, basic operation, that is the cuSparse is nearly 30 times slower than the dense operators. That's why the GPU time of transformation, although the flops is high, but the basic components is very highly efficient. So the GPU time is low. For the sparse aggregation, the cuSparse is very, very inefficient. So the GPU time is will need more than the transformation part. So how to deal with the sparsity? Now, we think that actually there are two ways. One way is using, still we can use GPU, but you need to design new kernels and tools for to maybe better, you need to be better than the cuSparse, right? So to improve the whole performance of the graph neural network. And the other one is you can design your own graph neural network accelerator. So in our group, we propose DG sparse, and the DG sparse library improves very large portion comparing with the cuSparse. And this is the operator level. So these very efficient sparse operators we design is the first technology. Then we propose the DG sparse wrapper, which is open source and provides more interfaces. So we can include cuSparse. And if you want to change your code, then you just include the wrapper, or using the wrapper is enough because we're including the cuSparse and also DG sparse. And results show that with all these, and we also provide a DGN layer, that is a GNN-based deep learning abstraction layer. And using all these technologies, we can achieve about 10 times system acceleration with a 10-time development efficiency increase. So now we are at this step. We are, when we are trying to develop this method, we are trying to submit some of the papers to different venues. And we are also talking to CUDA and to see, and PyG and DGL, if they can include our library. So then I will go inside the GNN accelerator design and briefly introduce the key insight or the ongoing research part of the GN accelerator design. So in the past 2 years, many articles or papers about GN accelerators have appeared in top conferences and journals in the fields of architecture, EDA, and programmable logic. You can see the FCCM, HPCA, and also the ICCAD and vice versa. So the relationship of these articles is showing, we are trying to show in this figure, and the purple numbers show the speed up of different studies. That means this one have this numbers of speed up comparing with this one. So it's a very interesting relationship. But there are roughly 2 types of GN accelerator. The one is the two-stage architecture. This two-stage architecture firstly proposed by high GCN, this high GCN here. As shown in this figure, the architecture implements 2 different cores for message aggregation and feature transformation in the graph neural nets. The first core consists of some SIMD engines, vector cores, and modules for sampling and scheduling. And the other one is systolic array architecture for neural network-like computation. It's just like the previous DN and the CN designs. The other one is the unified architecture represented by the InGN. As shown in this figure, this architecture implements a unified P array here, which can not only perform feature transformation, that is the matrix multiplication calculation, but also perform message aggregation, which can be considered as sparse SPMM, that is sparse matrix and multiplication like operations. The first problem, so we find out some of the key point in the GN designs, and we're trying to share with you. And the first problem is the utilization and the schedule. So which is mainly to be solved by the two-stage architecture. So unlike the convolutional neural network, which is mainly bounded by the convolution operation, which is the computation bound, the graph neural network contains 2 kinds of operations, and the calculation amount of 2 operations is very, very different in different models. So how to improve the utilization of the 2 cores if you are a 2-stage architecture? And a high GCN proposes that the systolic array can be designed to be more flexible and support different granularity working modes so as to increase the flexibility of scheduling and balance the resource utilization. Besides, it's also very, very important for the 2-stage architecture to support different orders of the data flow. In different graphic neural network models, the order of aggregation and transformation is not fixed. And when aggregation is a linear operation, the order of transformation and aggregation may be exchanged to reduce the total amount of calculation under some conditions. But in the high GCN architecture, the data path is fixed to aggregation first. So there are some other work, such as bifusion, propose some bidirectional data paths to improve high GCN and support more GN models. So the orders is very interesting things you need to look at. The second one is the workload balance. The workload balance is very important for computational efficiency. As shown in the figure, it is the statistics of the numbers of non-zero elements in a graph data used by graph neural network and in the sparse matrix of the sparse convolutional neural network. It can be seen that the graph neural network is more sparse and much more unbalanced than the sparse convolutional neural networks. So the most intuitive task mapping method of graph neural network accelerator is that one computing unit processes one row of the sparse matrix, which will lead to serious imbalance of the computing unit and affect the hardware utilization and slow down the computing speed. So there are some work such as the AWB GCN, which published in Micro 2020. They propose 3 hardware-based auto-tuning technology to solve this problem. The following figure is the hardware architecture proposed in this work. The main idea is to flexibly allocate tasks through a large number of exchanging data passes between PEs. So this is one of the try from the academia. And for the third key point is the data reuse. And graph neural network has 3 characteristics. One is large number of vertices, extremely sparsity, and the vector feature which make the data reuse more difficult than the convolutional neural network. As shown in the figure below here, it is the diagram of calculating aggregation in graph neural network. First, we need to load some of the features and then calculate the partial sum of group of output vertices. Due to sparsity, the data reusability of this calculation is very low. Then continue to read the input features. Due to the large number of vertices and vector feature, the amount of input data is large, but the on-chip memory size is very limited. So the subsequent read features will replace the original ones. After finishing the calculation of the first group of output vertices, we need to read the input features from the beginning again. This leads to the low data reuse of graph neural nets. So there are also some of the technology proposed for the data reuse problem, such as the degree-aware cache is a very useful solution to solve this problem. The main idea is that due to the power law of graph, the number of times that an input feature can be reused varies greatly. Therefore, when caching, we should try to cache features with large degree and replace vertices with small degree. By this method, we can greatly increase the average number of data reuse, as shown in the figure. It is the architecture proposed by GN here. Each P unit has an independent degree-aware cache, which greatly improves the data reusability and reduce the excess of DRAM. So I will talk a little bit about the future direction because we are also working on this part. So I think there are three things we need to consider in the future. The first one is for quantization and compression, which is very popular in convolutional neural network, should also be well considered in the graph neural nets. And the second is that the mini batch and sampling makes the data loader of GN more complicated than that of the convolutional neural network. And it should be considered in the accelerator design, how to design your hardware to meet the requirement of mini batch and sampling, which is the very interesting feature of the graph neural network. And third one is the scalability. So the graph is become larger and larger. So how could we solve the scalability problem of the accelerator is also a very important topic when people are trying to use the graph neural network accelerator. Okay, so in summary, we talk about a little bit about the deep learning. What is the deep learning? And it's widely deployed in many fields. And for the hardware part, it becomes very cost, and we need to lower the computation capacity and the memory consumption and improve the energy efficiency. So we try to talk about the software hardware co-design methodology for deep neural network design, which is you need to improve the peak performance of the chip and improve the utilization of your chip and to lower the workload needs by different technologies. So we talk about the convolutional neural network and recurrent neural network in different levels, such as software level, architecture level, and the circuit level techniques. And for now, we are looking at the embedded application, how to use the deep DNN accelerator in the embedded part, and how to use it in the cloud part. And more basically, we found the more fundamental part. We need to look at how it the data inside the neural nets, how they can be represented, if they can be represented by only 1 or 2 bits, or what is the limitation, and how these architecture of the neural net design and related to the hardware part. And when we go to even sparser, more sparse neural network, that is the graph neural network, we share some our view of the graph neural network design issues and the future directions. So I hope I can bring you some of the knowledge of the deep neural network accelerator design, especially on FPGA. Thank you. And if you have any questions. So any questions? Hello, can you hear me?
Yes, I can hear you, but I think there's no question.
Okay. Yeah, I put my email and website here. So if you have, okay, we have one of. Okay, the question is, how is the performance difference of deep GN I'm not very sure about DGNN in single GPU versus multiple GPU. So actually, we are not looking at for our experience, we are not looking at the GNN on multiple GPUs. So maybe I cannot give you a very good answer to this question specifically. But I do think the scalability of allocating or separate or split the workload of one DGNN to multiple workload on different GPU may cost some of the overhead here. So if a single GPU can handle it, we will not go into multiple GPUs. Actually, we are trying to look at how to reduce the memory requirement, and then we can put a large GN on one GPU. So the main, I think the main limitation is the memory or the graph memory on the GPU. I'm not very sure if I answer your question, but maybe we can talk more in the email, and I can share you some of our recent.
Hi.
Second, I see another question. Sorry, can you please mention the key factors that affects utilization ratio of the hardware? Actually, I think the memory, how to fit the right data to each of the PE, a processing element, or the multiplier is the key thing. So moving the data around is the key issue affecting the utilization ratio. Yeah.
Okay, does it mean that you're talking about the data flow mapping techniques? They are key to this, like the formulation of this utilization rates?
Yes.
Okay. Are there any other factors?
I think this is the key part.
Okay. Thank you.
Yeah. Because it related to your memory allocation and your communication, how you all the cores communicate, right? A lot of things about the memory flow. Yeah.
Okay. Thank you.
Hi, Dr. Wang. Thanks for the talk. So I've been, when you said XPUs, right? So I've been working on the optical neural network accelerators. Do you think the same three factors like the workload, peak performance, and the efficiency will be the key factors while designing them as well?
Sorry, what kind of process unit you are designing? Sorry, I didn't catch it.
I am trying to design optical neural network accelerators which perform vector operations in optical domain. So, but I wanted to know how important it is for the accelerator to take care of the workload as well, or it should be only concentrating on increasing the performance.
For optical part, because some of my colleagues are working on optical neural network accelerator or acceleration design, I think there are some of the key factors that they are looking at. One is the because this is optics is a kind of a streaming accelerator, and if you want to memorize some of the data, then you will cost a lot. And if you want to bring the optics and the electrics together, then you need to have the converter. Then that takes a lot. So these are two very important things. And the other very important thing, as we see, is if you they are trying to look at how to make it smaller or on chip. But if when we move the optical neural networks on chip, then the fading, that the energy, if you put the light on the chip, then it fades quite dramatically. So how to make a deeper neural network is also one of the key things. So I do think there are some of the physical limitations that need to be handled. And if you can trying to find out some of the ways using software technology to conquer this these physical or hardware problems, that will be very interesting.
Thank you, Dr. Wang. And one more question is, do your lab has any open source simulator for your work, which you have it open for everyone to use?
What kind of, we open some part of it, yeah, but for the compiler, we don't open this open source, but we have some open source simulator. For example, we have the NAS open sourced, and we have the simulator of ReRAM architecture level simulator open sourced. Yeah, so you can try to write me an email and we can check, send you the list of our open source, and you can let me know what kind of software you are looking at. Yeah.
Sure, thank you.
No problem. Yeah.
Well, thank you, Yu. Great talk. Hold on, let me turn my video on too. If there's are there any more questions from the audience?
Yeah, I thought this was very interactive, actually. Yeah, there is a lot of questions and it was very interesting. Thanks, Yu. This was very
thank you.
good
Thank
class.
you for inviting me. Yeah.
Oh, yeah, of course.
I think we can stop the recording now and then.
Yeah.